Hello and welcome to the study of this chapter, DC circuits, which means you're going to look at direct current circuits. So there are two types of currents. One is a direct current, the other is an alternating current. Direct or direct currents are produced by batteries. So that's what we're going to be focusing on in this chapter. So as you can see on this page, you see a complicated circuit that has so many components. Obviously, this is an audio amplifier circuit because at the end you see a speaker, a loudspeaker, and right there at the beginning you see an audio in, which could be a microphone. So these are resistances. You see that all these are resistances. Well, this is a capacitance. It's actually an electrolytic capacitor because it has a positive and a negative. And you see that the lines are not parallel. One of the lines is curved. So that shows it's an electrolytic capacitor. This is a transistor. You have a transistor here. 1, 2, 3. You have 4 of them. And then you have 2 diodes. These are transistors, and diodes are semiconductor devices. And then what is shown here is, of course, grounding. So it's grounded. So that means it's a negative terminal. So we're not going to look at all of these in this chapter, but this chapter paves the way to look at all of these later on. So let's get started. So as you move into this chapter, first of all, we have to take a look at the sources and the types of sources. So here you have a type of source. And what is a source? It's something that maintains one terminal at a higher electric potential compared to the other. So when we draw the symbol of a battery, we draw a bigger line, which is the positive, and then a shorter line, which is the negative. What it means is that whatever you connect to the bigger line is at a higher potential compared to what you connect to the lower side. So we call it positive and negative, but it simply stands for higher potential and lower potential. So that means there is a potential difference that is created by this battery. And when a potential difference is created, a current begins to flow. So that's why it's called a source. But then when we start looking at sources, we see that sources begin to have their own internal resistance. So all batteries tend to have an internal resistance of their own. And the reason is the current that flows through the outside of the circuit has to flow through the inside of the battery as well. So it creates an internal resistance to the flow of current. An ideal source, however, is defined as a source that has no internal resistance. An ideal source has no internal resistance, zero internal resistance. And in many of our problems, we will look at a battery that has no internal resistance. Okay? But as shown in this circuit, you can see that this is the battery. And this little r, which is the resistance shown, is actually the internal resistance of the battery. It's just shown outside. It's internal. And that's clear from this boundary that you see, the dotted boundary. That entire thing is the battery. So that's the internal resistance within the battery. And this is whatever needs to use that current. So it could be a light bulb, or it could be an electric motor, or whatever. But that is called the load, L-O-A-D, load. Load resistance is whatever intends to use the source. So that is caps R. So the load has a resistance caps R. Therefore, the total resistance in this circuit is the sum of the two. So it's R plus little r. And because they are connected in series, the current flowing through both of them are the same. You see the current? Currents always start out from the positive, flow through this, and through the load resistance, and back into the negative, and through the cell or through the battery. So since the currents are the same, These two are in series, and therefore to get the EMF of the battery, EMF is actually the maximum voltage that a cell can produce, when it's not being used. So when you buy a battery from the market and it's written 12 volt on that, that means 12 volt is the maximum that it can produce when you don't actually use it. But when you start using it, you see that it will not give you its EMF or maximum. It'll fall. Why? Because of the internal resistance. I'm going to show that using a little bit of math here. So as you can see, the EMF is I times R plus R, because there is a potential drop here. Remember Ohm's law, I times R is the potential drop here, and the potential drop across the load is I times caps R. So when you add the two potential drops, you're going to get the EMF of the battery, which is what is written there down. So EMF is I R plus R. When you distribute that, you get IR plus IR, and this I times little r is the voltage drop inside the battery, so it's called the lost volt. That means it's not available for the external load. That much is lost. So that's why it's called the lost volt. So that's an important formula to remember. What does this show? It shows that if the internal resistance is high, then you're going to have a bigger loss. So the lost volt will be higher. So we always try to keep the internal resistance low. For example, the internal resistance of a car battery is 0.01 ohms. See how small that is? That's why I've got to pay a huge price for that. But on the other hand, if you buy that dry cell from the market, from the store, that has an internal resistance of about 1 ohm. So it might be 1.5 volt, which is the EMF, but its internal resistance is 1 ohm. Compare that with the car battery, whose EMF is 12 volt, but the internal resistance is only 0.01 ohm. So here is an example where the EMF is 12 volt, the load resistance is 10 ohms, and the internal resistance is 2 ohms. So to calculate the current in the circuit, we would use I is equal to E by R plus R, because that's voltage by the total resistance. And on doing that, you get 12 divided by 10 plus 2, which is 1 ampere. And so the voltage drop across this load resistance is I times that resistance, which is 1 times 10. So that's 10 volt. While the voltage drop inside the battery is I times little r, which is 2 volts. So you see that 2 volt is lost. So out of the 12 volts that the battery is able to provide, we are only able to tap 10 volt while 2 volts is lost. Again, remember that to keep the lost volt to a minimum, the internal resistance has to be much smaller than the external load. Okay? So, moving on, we know that resistors can be connected chiefly in two ways. When you have multiple resistors, you can either connect them in series or you can connect them in parallel. So this represents a series combination of 3 resistors, R1, R2, R3, connected to a source with voltage V. And we're considering or imagining that there is no internal resistance for this battery. The current flowing is I through all of these 3 resistors. And that's important to know that whenever resistors are connected in series, the current flowing through them will be the same. But the voltage will be different generally. The voltage here would be V1, IR1. Here it would be IR2, and here IR3. And if you take the sum of the 3 voltages, you must get it equal to the voltage of the source. So that's what we're going to write. But before that, having that idea in mind, these three resistors may be replaced by a single resistor in such a way that the same current as before flows through it, in which case this resistance is called the equivalent resistance because it's equal to the other three. Why is it equal? Because it's carrying the same current as carried when the other three were connected. So in this particular case, we know that the voltage drop here would be what? I times R equivalent, which should be equal to the voltage of the source. So now let's look at these ideas that I've just spoken about. So remember, the same current flows through them. And so the total voltage is I times R1 plus IR2 plus IR3. Which is from this circuit. Now when you connect the equivalent resistance, now you can say IR equivalent is equal to IR1 plus IR2 plus IR3, because remember, IR equivalent is equal to the same voltage. So from those two, the I's cancel out, and then it's clear that the equivalent resistance is simply the sum of the three resistors. So whenever resistances are connected in series, the equivalent resistance is the sum of all those resistances. But now let's look at the other connection where you could put resistors in parallel. When you put resistances in parallel, the voltage across them stays the same. And the reason is, here there are only two resistors connected in parallel, R1 and R2, and you can see that individually, these resistors are connected to the source. What does that mean? This is the positive terminal of the battery. This end is the positive of the resistance. So you see how it's hooked up there? And the negative of the source is connected to the negative of that resistance. It's the same with R2. So R2 and R1 are independently connected to the same source, which means the voltage across them will be the voltage of the source. So in parallel, the voltages will be the same. Though it's given as V1 and V2 here, remember V1 is equal to V2 is equal to the voltage of the source. That means the currents flowing through them will be different. So the current through R1 is I1, the current through R2 is I2. So the voltages are the same, the currents are different. So now again, let's consider that there is an equivalent resistance which can replace these two in parallel, and the current flowing would be the same as before. What I mean is that would be the total current that came in before it split into those two currents. So if that's the case, what's the formula for I1? What is I1? I1 is V over R1. What is I2? V over R2. Okay? And if you add I1 and I2, wouldn't you get I? Yes. So if you had three resistors, that would be the same thing. When you add I should be equal to I1 plus I2 plus I3. So the currents always add up. So I'm going to write that. The voltages in parallel are equal, the currents are different, and when you add all the currents, you must get the total current. That's the basic idea. So I is I1 plus I2. And what is I1? Okay, I is V by R equivalent from this, and then V by R1 plus V by R2. The V's from the top will get cancelled. So you will get 1 by R equivalent is equal to 1 by R1 plus 1 by R2. So that is the formula that you use when resistances are connected in parallel. 1 by R equivalent is equal to 1 by R1 plus 1 by R2. We will use these formulas as we work out problems, but now let's look at this complicated circuit. Look at this circuit, which there you have four resistors and a source. And the source does not have an internal resistance. And we got to find the current that is sent out by the battery, the current that flows out of the battery. What actually happens is the current flows from the positive, reaches here, Okay, when it reaches here, it splits into 1, 2, and the same current that flows through R3 flows through R4. Why? Because there's no other path. Whatever current flows through R3 flows through R4, which means R3 and R4 are in series because the currents are equal. That means in place of 6 and 4 ohms, we could imagine there was a 10 ohm resistance connected there. So that's what you find here. See, 10 ohms in place of that. How did we make that out? Because the current flowing through them are the same. So now we replace these two resistances with a single 10 ohm resistance. And then start looking at that circuit again. You would understand that, okay, let's get to this point. When the current reaches here, it splits into one part that flows through R2, second part flows through the 10 ohm, which is the combination of 3 and 4, right? So that means generally these currents will not be equal. What does that mean? That means these two resistors are connected in parallel. That's right. If they are connected in parallel, then what is the formula? The formula is you have to take 1 by 10 plus 1 by 10. That will give you 1 by R equivalent. When you use that formula and calculate the equivalent resistance, you are going to get 5 ohms. It's simple because if you have two equal resistors connected in parallel, the equivalent resistance is always half of that, half of one of them. So 2 10 ohms is going to give you 5 ohms. So now that's your final circuit, and then look at the current again. Doesn't the current through 7 ohm have to flow through 5 ohm? Yes. So which means they are in series. So what is the total? It's 12 ohms. So finally we end up with this circuit. So now you have a 24 volt source connected to a 12 ohm resistor. What is the current? 2 ampere. By Ohm's law, current is voltage by resistance. So 24 divided by 12 gives 2 ampere. So the current that starts out from the battery is 2 ampere. And then we should be able to calculate the currents that flow through all the other resistors, which we will do later. But I'm going to show you a simulation of this circuit, and there I will show you the currents that flow through each resistance, because we're going to have to calculate the currents through each resistance later on using what is called Kirchhoff's laws. We'll get there. Okay, but I hope you understood this. This is how you simplify a complicated circuit. In transitioning, let me give you a practical phenomenon that all of us may have observed. That is, if a large appliance switches on, what I mean by a large appliance is a refrigerator or a motor, as shown in this diagram, a motor or a refrigerator switches on, suddenly you see the lights go dim. How can that be explained? The large appliance has a greater power, requires a greater power. So it draws a huge current. And when it draws a huge current, that current is now flowing through the connection wires, isn't it? Connection wires usually have a low resistance. But since the current is now big, the product of the current and the resistance of the connection wires becomes considerable. That means it's not negligible. So again, the big current drawn flowing through the small resistance creates an appreciable voltage drop across the connection wires, so the other appliances don't get that much voltage. That's why you see the lights dim. That was just a pointer, to give you a practical idea. Now let's move on to what I told you before, trying to calculate the currents through every resistor in a complicated circuit. Now what did I say we use? We use what's called Kirchhoff's rules. And there are 2 rules, and these are very important. Well, will be asked on every exam, so you need to know how to apply this. The rules are simple. Here is the first rule coming up in Kirchhoff's rules. The first rule is called the junction rule, because it's to do with a junction, and simply states that the total current flowing through a junction is 0. So that is Kirchhoff's first rule. The total current flowing through a junction is zero. What does that mean? Now, when you look at an electrical junction, there will be some currents flowing in and there will be some currents flowing out, right? The total current coming in will be equal to the total current flowing out. That's what's written here. The sum of the currents coming in is equal to the sum of the currents flowing out, which means that the net current is zero, coming in as positive, going out as negative. The significance of Kirchhoff's junction rule is that there is no stagnation of electrical charges at a junction. No stagnation. Charges don't stay at a junction. Whatever comes in goes out. That's the significance of the first law. So in effect, it's the principle of conservation of charge. Now to the second rule. In the second rule, the total voltage through any electrical network. So now we're not looking at a junction, we're looking at a network. So a particular branch of the circuit. When you take all the voltages across every component and add them up, you will get zero. So now the total voltage along all the components is zero. And this is just the conservation of energy. Energy cannot be created nor destroyed. It's simply the significance of this law. So you see that the total voltage is zero. Now, when it's stated, usually we use these words, the algebraic sum. That means you have to consider the sign of the voltages. Some voltages are going to be positive, some are going to be negative. And so if you understand that part from the example that follows, you are good. So let's go there. So this is to illustrate the junction rule. You see that the currents coming in are I1, I2, I1, I2, I4, and I5 coming in. I3 and I6 are flowing out. So the total currents coming in is equal to the total current flowing out. That's simple enough. Now to understand the second rule, which is a little bit harder, we have to consider a network. So here is our network. So now, this end of this resistance, let me stop that. This end of this resistance is going to be what? Positive, because it's connected to the positive. This end would be negative. This end of the resistance, second resistance, R2, will be positive. This will be negative. Follow along. For R3, this end will be positive. This end will be negative. Easy to understand because that's connected to the negative. So, if you decide to go from A to B, so A, B, C, D, A, that's the name of the loop because the loop has to be closed. So A, B, C, D, A. If we decide to go from A, you start the journey here. You're going from negative to positive. So you would say plus 12. 12 is the voltage of the source. So you would say plus 12. And then you're going from what? Positive to negative. So you would say minus I1, IR1, minus IR1, where I is the current. See, the current flowing through these three are equal, correct? So the current through R1 is I. The resistance itself is R1. To get the voltage, you multiply I with R1. But since you're going from positive to negative, you would put that as minus IR1. And then come here, again, it's minus IR2 because you're going from positive to negative. And then when you get here, it's again minus IR3 is equal to 0. So what did I say? Let's say, see that again. Plus 12, because you're going from negative to positive, plus 12 minus IR1 minus IR2 minus IR3 is equal to 0. Okay, isn't that what I've written here? What is coming up here is, okay, I changed that just to make it like I told you. Is that? Yes, The only thing that happened here is I changed the signs of all of them. It doesn't matter. In any equation, instead of having 3 negatives and 1 positive, I just switched the signs of these 3, made them positive, and this is negative. I hope that makes sense. Well, you can leave these 3 as negative and keep this as positive. So that is the application of Kirchhoff's voltage law. Okay, let's work out an example. Look at this circuit. When you study the circuit, you have this battery, V volt, R1, R2, R3. Okay, as you start from here, there is a current I1 that flows through R1, but when that current reaches here, that splits into I2 and I3. So when you apply the junction rule at junction B, it's very clear that I1 is equal to I2 plus I3. Yeah, whatever comes in is equal to what flows out. So I1 is I2 plus I3. Let me complete that. I hope that's clear. Plus I3. Okay. Another thing is, see, the current I2 comes in here, I3 flows through R3, and then if you look at junction E, I2 and I3 are coming in, so I2 plus I3 is again equal to I1, which is the same thing what we got here. So that's the application of the junction rule. Next, let's apply the voltage rule. When you apply the voltage rule, I'm getting I1 R1 plus I2 R2 is equal to V. So where have I applied it? Which is the network? Actually, I'm taking I'm using A, B, E, F, A. A, B, E, F, A. So if you start from here, you're going to go plus, because you're going from negative to positive. So you're going plus V. This would be, tell me, isn't this the positive of the resistance? This end is going to be the negative. How do you know this end is the positive? Because it's connected to the positive. So if you go this way, you're going from positive to negative. So it should be minus I1 R1. I1 is the current, R1 is the resistance. So it's minus I1 R1, same thing here, minus I2 R2 plus V is equal to 0, which is what I've written here. I just made the 2 negatives positive and took this to the other side. Write it down clearly and check it out, okay? And then if I once again apply Kirchhoff's voltage rule or loop rule in this mesh. Oh, I use the word mesh. Mesh is another word for network. So now I'm going to look at the mesh B, C, D, E, B. B, C, D, E, B. Okay. So before I show you, what are we going to get? Let's say we start from B and then go this way. This end is positive, right? Yeah, because it's connected to the positive. So this end is positive, so we're going negative, what's the current through this? I3. Yeah, this current I3. So negative I3 R3, keep going. Now you're going from negative to positive. Look at that. This end is negative, this end is positive. So now you'll have to say plus, what's the current? I2 R2 is equal to 0 because there is no voltage source in this mesh. Once again, negative I3 R3 plus I2 R2 is equal to 0. So that's where, that's what you get when you apply the loop rule in that mesh. Okay. There. I just decided to bring the voltage to the other side. So now I'm just giving an example of what if the voltage is 5 volt here, the resistances are 3, 4, and 1. Okay? So this is 3, this is R3 is 1, and R2 is 4. Then would you be able to calculate the currents? For sure. So you would now get 3I1 plus 4I2 minus 5 is equal to 0. That's like what I told you before, just that I'm using numbers now. And then I3 minus 4I2 is equal to 0. And we're trying to get simultaneous equations, but you see, you have three variables, I1, I2, and I3. Do you see that I1, I2, and I3? So we need to get rid of one of them, and which we can easily because we know that I1 is I2 plus I3, don't we? So we'll break this I1 into I2 plus I3 and then solve the simultaneous equations. So that makes it 3I2 plus 3I3 plus 4I2 minus 5 is equal to 0. And then 7I2 plus, yeah, because that's what you get. You get 7I2 because you have 4 there, right? Oh, here 4 and 3, so 7I2 plus 3I3 minus 5 is equal to 0. Okay, so that is one of your equations. And then you have, I've written that there. So you can solve it any way you like, but what I did here is actually I multiplied this equation with 3, negative 3. The idea is if I multiply this with negative 3, this is going to become negative 3I3. This is positive 3I3. So if I add them, it'll cancel out, see? But I got to multiply this with everything. So don't forget. So this will become 12I2. And then I have 7I2. When I add them, it's 19I2. Correct? 19I2. And then minus 5 is equal to 0. So if I rearrange that, I'll get the value of I2 as 5 by 19 ampere. Once you get the value of I2, you can substitute it into the equation, one of the equations, and solve for I1. So here is another circuit where I'm trying to demonstrate how to use Kirchhoff's rules. Okay, so here is a circuit. In this circuit, you have several sources. You have V1, you have V2, and V3. You have several sources, and you have 6 resistors. And you need to find the current through each one. So what I first did is I labeled the positive and negative of each resistance. Like this end is connected to the positive, so that's positive. This is negative. Hope you understood that. This resistance R3 has the negative of the battery connected here, so that's negative. This is positive. Same thing. Didn't I label it here? I think I did. Okay, let me run that. No. So this end here, it's going to be positive. This is going to be negative. And this one likewise is negative. Here it's positive. This is going to be positive because it's connected to the positive here. And you may have an argument on that. You might say, hey, this is a negative. This is a positive. Okay, so this is positive and this is negative. So first, let's consider, the junction rule. Let's try to apply the junction rule at F. It's quite easy. I3 is coming in while I1 and I2 are flowing out. So I3 is equal to I1 plus I2. Got that? I3 is equal to I1 plus I2. And then we will try to apply the loop rule in the outer mesh. The outer mesh, excuse me, is ABC. You see that A, B, C, D, E, F, A. So the outer mesh. And we will start from here. This is resistance R1, and we're going from positive to negative, aren't we? So that'll be negative I1 R1, right? Skip this for the time being. Negative, what's the current? I1 R4. Yeah, that's the same current I1 flowing there. I1 R4. And then you come here. What's the current here? The current in this mesh, it's I2. Be careful. Because you see the I2. Okay. And this end is what? Is negative. This end is positive. So now we're going plus I2 R6. Here, plus I2 R5. Here, plus I2 R2. So you heard me give 3 terms with I2. And what I'm going to do is, as you can see down here, those three are collected together. And then you have two terms with I1, which are those. Negative I1R1, right? Negative I1R4. So those two terms with I1 are connected together, collected together, and the three terms with I2 are collected together. One thing is very clear, that if this is negative, and the others are all, see, positive, do you see? So they have opposite signs. So that's why. And then what about the source? When you look at the source, in this one you're going from negative to positive, so it'll be plus 0.5. And then when you come down here, it'll be minus 2.3. So it'll be plus V1 minus V3. So their signs are, so you have to really, listening to me will not be enough. You have to try to write it down on your own, and then you will see it. There's no other way. So if you write that, you're going to get this. If you write this carefully, you're going to get plus V1 minus I1. See what I'm writing? Minus I1 minus R4. And then plus R2 times R6 plus R5 minus V3 is equal to 0. Stop. Did I miss something? Plus I2, R6, R5. I think I missed R2 when I wrote it. I missed that. And then I1 times R1 plus R4 minus R2, I2, R6 plus R5 is V1 minus V3. Sorry, I again missed this resistance, which is actually given here, but I forgot to write that. So keep that in mind. I'll add an annotation, but for now I've missed it. Okay, so that's how you solve it. Once you get those equations, you can substitute and solve. All right, next let's look at the combination of cells in series and in parallel. So the circuit that you see, you have two cells connected in series. And so usually we call a cell a battery, which is wrong. It's actually a combination of cells that should be called a battery. So you have two cells connected in series. And here is the schematic of that. Battery 1 has an EMF E1, internal resistance R1. Battery 2 has an EMF E2 and an internal resistance R2. And then they are both driving a current through a load resistance caps R. So when you look at the circuit, what's the total EMF? The EMFs are going to add up. So you're going to get a total EMF of E1 plus E2. But the bad thing is that the internal resistances also add up. So the total resistance in this circuit is going to be R1 plus R2 plus the load resistance. So once we have the total EMF and the total resistance, we can represent the current using Ohm's law. So we're going to get the current I, because I is the current, as the total EMF divided by the total resistance. So the current I is the total EMF, E1 plus E2, divided by R1 plus R2 plus R. That's all. And remember that we'll never put this cell opposite. I mean, we won't flip this. Never. Whenever you connect cells in series, you're going to have the positive of one in contact with the negative of the other. That's why we draw the diagram the same way. Watch. It's a negative, positive, negative, positive. See that? So that's how we draw that, and that's how we connect. Because if you flip one and connect it the other way, they'll be opposing each other. That makes no sense. Okay. So when you add cells in parallel, as shown here, what's going to happen is, you have to remember two things. Whenever you connect cells in parallel, the currents add up, okay? But before we get there, you have to remember that always the cells connected in parallel should have the same EMF. So E1 and E2 should be equal. We cannot have a 6-volt cell connected in parallel to a 4-volt cell. We can't. You'll see why. Okay, but for now, if you look at these two EMFs and you have their internal resistances. So what is the internal resistance of these two? They are in parallel. All three are in parallel. So how do you find the total resistance? It's 1 over R equivalent, remember? It's 1 over R1 plus 1 over R2 plus 1 over caps R. When we use that formula, the equivalent resistance is going to be really small. That's the advantage of connecting cells in parallel. When the equivalent resistance is really small, you're going to get a huge current flowing. So whenever you need a big current to flow, that's when we would combine cells like this in parallel. Even otherwise, you can see that the currents I1 and I2 add up and flow through the load. So the current flowing through the load is a huge current. All right, let's write down the math. Remember that the currents always add up in this case. And the current through the load, because we're interested in the current flowing through the load, is given by E. Oh, wait, why only E? Didn't I tell you that E1 must be equal to E2? And the total EMF is simply E. So if you had 10 of these batteries connected together, or 10 of the cells, and all of them had the same EMF, but you had 10 of them, the total EMF would simply be just the EMF of one of them. So whatever you connect, how many ever, or 100 or 1,000,000, the EMF available is going to be the EMF of one of them. So that's important. Divided by the R equivalent of these two. So these two are in parallel, while that combination is connected in series to this resistance R. So don't misunderstand what I said before. So that means the R equivalent of these two plus the external load, right, which simplifies to, okay, remember E is E1 is equal to E2. So 1 by R equivalent is 1 by R1 plus 1 by R2. We know that. And then internal resistances are what? Usually small. And since the internal resistances are small, and now on top of that you've connected them in parallel, the equivalent of them becomes even smaller. That's why the current becomes bigger. So that's the difference between connecting batteries in series and in parallel. To just summarize, when batteries are connected in series, the EMFs add up. All right, next, I briefly want to talk about two measuring instruments. One is an ammeter. It's used to measure current. The second is a voltmeter, which is used to measure voltage. First, let's look at an ammeter. You can see in this circuit, here is the ammeter, and you want to measure the current through this resistance. If you want the current to be measured, you want the same current to flow through the instrument. So you have no option. You have to connect the ammeter in series with that resistance. Why? Because in series is when the current flowing are equal. So again, if you want to measure the current through any resistance, you have to connect an ammeter in series with that resistance, so that the same current that flows through the resistance which you're trying to measure will also flow through the ammeter. It's very important. But then again, when you do that, wouldn't the resistance in the circuit be changed? You don't want that to happen. The introduction of the ammeter should not change the resistance in the circuit, because then it will measure a wrong current. Therefore, the ammeter is a very low resistance instrument. In fact, its resistance would be like 0.01 ohms, even smaller. So the introduction of the ammeter has negligibly changed the resistance and the current in this circuit. So two things to remember. An ammeter is always connected in series. Number two, an ammeter is a low resistance instrument. So remember that. So here again, if you had another circuit like this and you wanted to measure the current through R1 and R2, see that? Then you would need two ammeters. One in series with this and the other in series with this. So now you would need 3 ammeters because you want the current through the battery, you want the current through R1 and the current through R2. And I've also written that ideally an ammeter has 0 resistance. Okay, that's the ideal condition. Practically, ammeters have very low resistance. All right, the second one is the voltmeter. And what is the voltmeter used for? It's used to measure voltage. That means you got to connect it in parallel to the resistance. So if you want to measure the resistance, you want to measure the voltage across this resistance, you got to connect a voltmeter in parallel with it. Why? Because we know that anything connected in parallel, the voltages are equal. Same here. And another here. See that? So that'll give you the voltages across those 3. But then again, you do not want the voltmeter or the introduction of the voltmeter to change the voltage in the circuit. Okay, so how should the resistance of the voltmeter be? The resistance of the voltmeter should be ideally infinite. Why? Because whatever current was flowing here, see that current I that was flowing before the introduction of the voltmeter, that entire current was flowing through R1 and R2, isn't it? When you introduce the voltmeter, you want about the same current to still keep flowing, which means the resistance of the voltmeter should be really high. Why so? Because if it's really high, only a small part of that current will flow through the high resistance path. Because currents always favor low resistance path. So I hope you understood that. So to summarize, a voltmeter is always connected in parallel to a resistance, and a voltmeter has a huge resistance, ideally infinite resistance. Okay, so those are the 2 points that you have to remember about voltmeters. So I hope you understood the difference between an ammeter and a voltmeter and the difference in the way they are connected in the circuit. All right, so the last part. All right, something in my eye. The last part of this chapter is where we talk about charging a capacitor. How do you charge a capacitor? Using a battery. So, but if you take a battery and I have a capacitor here. I just wanted to show you. This is a capacitor. The black cylinder that you see here is a capacitor. See? It says 100 microfarad. I don't think you can read it. It says 100 microfarad and then 50 volt, 250 volt actually, 250 volt, 100 microfarad. So that's a capacitor. And if you want to charge a capacitor, you cannot directly connect it to a battery because it'll blow up the capacitor. You always want to charge a capacitance slowly. When I may say slowly, as slow as possible. So you always connect it through a very high resistance. So to charge a capacitor, you always connect it with a high resistance. So that is going to give us, okay, that's a formula. So here we have the circuit. This is actually a multiple key that you see here. If you put this key in contact with A, then this capacitor is going to get charged through the resistor. See that? But after it gets charged, if you move this switch from A and put it in contact with B, now there is no voltage source, and so the charged capacitor is now going to discharge. So we're going to look at charging a capacitor and discharging a capacitor. So that's the first circuit that you have, charging a capacitor, and then you have the discharge of a capacitor through a resistance. And in order to get the equation for charging and discharge, we have to use Kirchhoff loop rule. So listen to me very carefully. At any instant during charging, let's say that the current through the circuit is I. So that current is growing, right? The current, is changing. Let me say it's changing. So when the current is I, at that instant, let's assume that the charge on the capacitor is Q. Because initially the charge on the capacitor was 0 and it's slowly building up. Right now it's reached Q. So the situation is the current through the resistance is I and the charge on the capacitor is Q at that instant. So what's the voltage across the resistance? It's I times R. What is the voltage across the capacitance? It's Q by C. If you add those two, you must get E. Isn't that Kirchhoff's loop rule? Yes, it is. So I'm going to write that. E is equal to I times R plus Q by C. Oh, I'm using caps Q, not a big problem. I hope you understood that. But when we look at this, we don't like this because there are, look, I is a variable, I is changing, Q is changing. We don't want two different variables, but we can easily represent I in terms of Q because we know I is dQ by dt. Current is the rate of flow of charge. So since I is dQ by dt, I'm going to make that substitution, which gives us E is equal to R dQ by dt plus Q by C. Then we have to rearrange this in such a way, because we are actually trying to get an equation for Q. We want to know how much charge the capacitor assimilates in a certain time. So we want Q as a function of time. So that's where we're going. So I'm going to use a little bit of algebra to separate the Q onto one side, and I think you can see what's happening. Took Q by C to the other side first, so it became E minus Q by C. Next, I'm going to take the LCM here, so it'll be CE minus Q whole divided by C is R dQ by dt. Manipulation of this, and then I have C minus Q is I took the C to the other side, became R times C. All right, almost there. Or dQ by C E minus Q. See how I collected the Q terms now? You see that dQ by C minus Q is dt by R. Now I'm ready to integrate. Integrate both sides. On the left side, the limits will be 0 to Q, right? 0 to Q. Because at time t is equal to 0, the charge on the capacitor is 0. So 0 to Q, and on the right side, of course, 0 to T. So we're going to do that integration, and let's see what you get. So integral 0 to Q of dQ by C minus Q is equal to integral 0 to T of dt by RC. All right, here you're going to get natural log and a negative because you have negative Q. So natural log C minus Q is equal to T by RC. RC is a constant, so it's easy on the right side. Next, substitute the limits. First, in place of Q, we will give Q, and then we will give 0. So that'll bring two terms, and then you're going to get something like log A minus log B, which you know is log A divided by B. Okay, there you have the two terms. Be careful about the two negatives. One is the negative between the upper limit and the lower, and then you have that. So there's also a negative here because this whole thing is negative, okay? Do that carefully, and then you see this becomes natural log C minus Q by C is equal to negative T by RC. And instead of writing natural log on the left side, you can write the opposite function on the right side. What's the opposite function? Exponential. So e raised to. So I'm doing that. And I also divided the C by C is 1 minus Q by C. And then I cut down one or two steps, but you can easily understand. So I get my final relation. Q is CE times 1 minus e raised to minus T by RC. But wait a minute. What is C times E? Oh, C is the value of the capacitance and E is the EMF of the battery. When you multiply capacitance with voltage, you get what? You get charge. So that's going to be the maximum charge. So you could put this as Q sub M, showing maximum charge. So that's the formula for charging of a capacitor through a battery. Let's discuss that. Charging. And I just wanted to, let's go back one more time. You see that you're dividing T by RC. That means both of them should have the same units. because exponential raised to can only be a number, so they should have the same units, which I'm trying to show here. Resistance is ohms, capacitance is farad, but ohm is volt by ampere, and farad, remember, coulomb per volt. So the volt cancels out from both sides, and then you have coulomb per ampere, which is actually second. Why? Because ampere is coulomb per second. That's why. So you have coulomb divided by coulomb over second, which the coulombs cancel out and they get second. So, and in fact, the product R times C is called the time constant. It's called the time constant of the circuit. Look at the definitions. It'll be the time for the charge to build up to, 63.9%? 63.2%, I'm forgetting. 63.2% of the maximum charge, okay? So that's we'll look at the graphs and then you will understand. So look at this. This is the graph. It's an exponential graph. Time on the x-axis, charge on the y. The charge starts from 0, but it builds up exponentially. This is the maximum charge. Remember, CE is maximum. And tau here is time constant. So after one time constant, the charge becomes 63.2% of the maximum. See? Look at that. And if that's the variation of charge through the capacitor, look at the variation of current through the resistance. The current actually decreases because when you first switch on, the current is big. But as the capacitor accumulates more and more charge, the current in the circuit falls. See that? It's an exponential fall. The voltage, of course, increases. Voltage across the capacitor increases, while the voltage across the resistor decreases exponentially. So if that is the formula for charging of a capacitor, what would be the formula for discharge? Discharging, it's easier to get the formula. Let me see if I wrote that down. For discharge, well, this is for charging, and I've just explained how you get time constant. If you substitute T as C times R, be with me. T is C times R. Wouldn't you get e raised to negative 1 here? Yeah. And then you plug in the value of e raised to negative 1. 1 minus that will give you 0.632. So C times R is called the time constant. Can we move on to discharge? Let's see if I also found an expression for time here. For current. So current is dq by dt. So I use d by dt of that. Okay, and then I got qm because it's a constant taken out. Then you have 1 by cr e raised to minus t by cr. Calculus, yeah. So that is, remember qm is ce. So ce times 1 by cr. The c's will cancel out. You will be left with E by R. What is that? That's current. That's why I have I naught. So you see the expression for current is different from the expression for charge. You see 1 minus here, you don't. So that's why as the current increases, the charge increases, the current decreases. The expressions are different. For discharge, the graphs are going to look like this. The charge falls, but the current increases. It's the exact opposite. While the voltage across the capacitor decreases, and the voltage across the resistance also decreases. Think about that. And here is the equation for discharge. Is that the same? No, it's not. The 1 minus is missing. I have not derived it. It's easy to derive it. Easier than the first one. So you get Q is Qm e raised to minus t by cr. In this equation, if you put t is equal to cr, what are you going to get? You get e raised to minus 1, and then Q is equal to Qm raised to e minus 1, and then Q by Qm will give you, because exponential raised to negative 1 is 0.368. So once again, we see that during discharge, you could actually look at this diagram carefully. You can see after one time constant, the charge has fallen to 36.8% of the maximum. And then I found the expression for current like before. This is what I get. So that's charging and discharge of a capacitor through a resistance. So that is this chapter. This chapter has many parts, and you got to really understand all the parts of this chapter. This is one of the more important chapters for your exam. Thank you. I hope you understood the concepts in this chapter, and then you will be able to do good on the exam. All right. This is me signing off. See you on the next video. Thank you.